Okay, it's 5:30, so let's go ahead and get started today. Good evening, everyone. How's everyone doing today? I wasn't talking to you, Kat. I was talking to my class.
Thank you. How are you, Professor?
I'm good. I'm good. Tired, but it's it's that time of the semester. So glad everyone's doing well. Okay. So the plan for today is I'm going to finish up our last lecture notes on frame equations. So there's not much left, so it's not going to take the whole time today. And then the rest of the plan for today, actually the plan for the rest of the week, was to start talking about the Matlab. So after today, we're basically going to cover everything I wanted to cover with regards to the direct stiffness method. So that's kind of the theme of this first part of the semester here and for the first midterm. And so in addition to we've been spending a lot of time learning the theory and doing a lot of hand calculations, but because this is a graduate level class, like we talked about at the beginning, that a big part of this is going to be a big part of the class is also learning how to actually implement this in the code. And so the reason I started this class with direct stiffness, even though in reality it's not used, this is not the method that's used in like ANSYS or other commercial programs, is that it provides kind of a really nice starting point, not only for the theory, if you've never seen finite elements before, but in implementing it in code, it's actually it's simpler than doing kind of a full finite element code, which is what we're going to be working on for the second part of the class. So, but even then, still, like a lot of the same principles and a lot of the structure of the code is going to be the same. It's just there's just some additional complications with kind of the more general finite elements. But I think just for now, with the direct stiffness, I think this is a great kind of starting point for learning the theory and also implementing the code. So that's kind of the plan for this week. Okay. Okay. And so the other thing I want to talk about today before we get started is our midterm. And so our midterm is going to be next Wednesday. And the format of the midterm, I don't know if I told you guys yet, but the format that I'm planning for the midterm is basically just going to be a 24-hour exam. And so basically what's going to happen is that I'm going to open up the exam at 5:30 p.m. Next Wednesday. So the date for that is October 7th. Okay. And so on October 7th, and actually let me start writing on the next page. Okay. So our midterm, the date for the midterm will be Wednesday, October 7th. Okay. And so that's a week from Wednesday, so 9 days from now. And the way, kind of like what I said, it's going to be a 24-hour exam. And so basically at 5:30 p.m. on this day, I'm going to open the exam on Canvas. And so I'm actually going to use the tools within Canvas. So it'll be kind of like a quiz that you would take like an online class. And basically you'll have until 5:30 p.m. on Thursday, October 8th, in order to submit your answers and turn the midterm in, basically. And so, kind of the reason I do this 24-hour exam, I know, a lot of faculty are doing very different things, and every faculty has their different opinions on this, but I like the 24-hour exam just because it's, it allows me to kind of write an exam of the same length and the same difficulty that, that we would have in the class, which is nice because I already have templates for all those things, so I can just basically just use those. But I think it also is just that it's I think it's important also, I think, to give you guys kind of flexibility on how you can take the exam, because I know during these really challenging times that it's everyone's schedule and everyone's kind of responsibilities are really different. So I want to make sure that everyone has the time to not only take the exam but also to upload the solutions too, because I know that takes some time as well. Okay. So the question in the chat is, how long should the midterm take if we were to do it in one sitting? So I'm designing this midterm such that it's to be completed in one class session. So I would set aside at least 75 minutes to like kind of sit down and do the exam, but definitely take advantage of more of the time that you need to kind of check your answers and submit it. If you've taken an exam on Canvas before, I know that they have kind of their in-quiz timer where you can only have the exam open for a certain amount of time. So I'm not going to turn that on. It's basically just going to be just the real life clock of like, 5:30 p.m. on Wednesday until 5:30 p.m. on Thursday. So you just have that 24-hour window to do the exam or not. All right, question. So I don't know if he answers or not, but are you going to want to see values in each matrix, or do you want to see symbolic values and compute after? So I think the way I'm going to do the exam is that basically I'm going to have you guys, basically the way that we've been doing all these problems. So that I want you guys to write out just the numerical value form of all the element stiffness matrices, and then I want you to show me the global stiffness matrix, and then apply the boundary conditions. And then I guess, because you're taking it home, you'll have Matlab, so I can ask for the solutions too. But if this were something that we would take in class, I'd probably have you stop at that point, because there's no way for you to kind of solve those big things unless you have like a graphing calculator. But those things are, I don't want to kind of leave it up to those kind of things and what calculator that you have. So so basically that's kind of my expectations for that. And we'll talk more about the format in a second, but I just wanted to start with just just the time frame and kind of the length of the relative length of the exam. Are there any questions on this? Any other questions? I mean, okay. And so one other thing that I'm going to do. Really taking advantage of this virtual thing, which, I might do this more in the future too, is that in this class, I really wanted to pack the schedule with, everything that I think you guys need to know about finite elements. So theory, code implementation, and also, some ANSYS as well. And so because of that, normally I didn't pack enough time to do review sessions for the exams, which I typically do for my undergraduate classes. But because we're in a virtual setting, we don't always have to be here at the same time in order to have a session. And so what I can do is I can pre-record a review session. I don't want to hold an extra class, because I know that everyone has busy schedules, and I don't want, some people that can make it and some people cannot. So I just want to make it fair. I'm just going to basically pre-record maybe like an hour 10 minutes review session, so that you guys can have that in addition to studying as well. So does that sound like a kind of a good compromise between in class versus no review session?
That sounds very thoughtful. Thank you for that, Professor. Great.
Okay. So I'll work on that. So I'll try to get that up. I still need to grade your homework 1, so that's on my to-do list. So I'm going to grade your homework 1s, and then before the end of the week, I'll have the review session posted, and I'll send an announcement through Canvas on that as well. Okay. I guess it's not really a review session; it's more like a review video. And so the other thing I always provide my classes before a midterm exam is a study guide, and so I should get that up, probably by tomorrow. And the study guide is going to be nothing more than just a collection of all the learning objectives we've covered so far. And so I like to do that just because it's kind of nice to have it all in one place. So that you can expect that to come up pretty soon too. Also, for the exam, there's going to be no ANSYS on the exam. It's just purely just on the kind of the hand calculations on the direct stiffness that we've gone over. And there's going to be no, beyond just solving a linear system of equations, there's going to be no MATLAB on it either. So I know starting today and on Wednesday, we're going to start, learning how to actually implement a full functioning finite element code. You won't have to know that for the exam. So that's purely just mostly in preparation for the final project that we're going to do much later in the semester. Okay. And so that's all the review stuff. So let's talk format. And so the way I like to break down my exams is that I kind of have it to be almost an even split between conceptual questions versus like actual computation problems. Right? And so there will be 4 short answer questions. Okay. And so these short answer questions will be kind of conceptual in nature. And so they're basically going to ask you, to answer something within 2, 3, 4, 5 sentences. And they'll be based on just kind of the theory and the concepts that we went over in the class. And this will be worth 40% of the points. Okay. So I think I've always thought that conceptual understanding stuff is really important, because once you leave this class and you go out and be professional engineers, it's very hard, I think, to remember the exact details of all the equations and the computation that you did. But I think one thing that you do remember is like kind of the intuition and the conceptual kind of foundation that you build from your class. So that's why I really tried to emphasize that a lot. And so the rest of the problems in the exam will be computation problems. Okay. And so far in this class, we've only just done kind of one kind of problem. It's just, here I give you a structure made up of, springs, trusses, beams, frames, and I just want you to solve for the finite element solution. So you can expect, the problems to all kind of look like that, basically, because we haven't really done anything else. And that's going to be worth the rest of the 60% of the points. Okay. Trying to think. Oh, okay. So so next Wednesday, obviously, we'll have the exam, so we're not going to have lecture. But I will pop in on the Zoom call if you do want to come in and ask a question. I'll be here during the duration of the lecture, so you can do that. But even after the lecture, like if you have questions, you have questions you're working on at night or the next day, you can email me the questions. And I'm always happy to respond. Or if you're on the Discord, you can private message me on the Discord as well. And I'd be happy to answer you there as well. So, just like in the exam, it's when you ask a question, it kind of has to be just between us, unless it's something that I want to make available to the whole class, and then I'll send an announcement through that. But that's kind of the mode and how you can ask questions. Okay, so the question in the chat is, I suppose homework 2 is also part of the midterm. Yes, and so the midterm is going to cover springs, trusses, beams, and frames. And so homework 2 gives you kind of the practice with beams and frames that you guys haven't practiced yet. So definitely homework 2 will be on the exam. Okay. And so I think that's everything I can think of about the exam. So are there any questions regarding this? Okay. Again, so the study guide will be up probably sometime tomorrow. And then we'll go from there. Okay, so that's everything with the exam. So let's go back to frames. Okay, so we had just one more. Oh, question. So any ANSYS related questions on the midterm? I might ask you a conceptual problem on ANSYS, but you won't have to open up ANSYS and do anything in there. Yeah. Okay, and so when we left off on last Wednesday, we were doing an example with distributed loading. Okay. And so our problem looked like this. Okay, so we had a 2-element system. And so we had element A right here and element B. Okay? And all of these are frame elements. Right? And so we had 3 nodes because we have these 2 elements. So we have 1, 2, 3. Okay. And then this length right here was 40 feet. This length right here was 30 feet. Okay. We have some properties. So we have the Young's modulus is 30 times 10 to the 6 psi. We have A, which is equal to 100 inches squared. And then I equals 1,000 inches to the 4th. Okay. And so those are all the parameters. And then in addition to these, we also had a distributed loading. Okay. And so we had a distributed loading on element B right here. And the value for this was 1,000 pounds per feet. Okay. And this is our W of X. Okay. All right, so this problem, just like every other problem that we've been doing, is we want to solve this finite element system for the deformations at the nodes. Okay. And since all of these are frame elements, we're going to have three components of the deformation. So we're going to have displacement in the x, displacement in the y, and the rotation. So we have 3 degrees of freedom per node here. So we have 3 nodes times 3 degrees of freedom. And so we're going to solve for 9 things overall. And so our global stiffness matrix is going to be basically 9 by 9. Okay. And so the first thing that we had to do, which we did at the end of lecture last time, was convert this distributed load into nodal loads. Okay. Right. Remember, the reason that we did that is because just the finite element framework that we have so far, it works best when we can apply our forces and our moments at the nodes in our system, because then we can just plug them right into our global stiffness matrix. Okay? And so the way we do this is we use the principle of equivalent work. And there's not there. We went through that process last time where you basically plug in, your load function, you plug in your uy of x, which remember is our assumed form. It's that cubic, really nasty function. And then by solving that, we get the coefficients, right? And then we end up with the following results. Okay? And so the derivation the computations for this we did last time, but since we're continuing this on, I'm just going to write the solutions. And so our distributed load here acts on, nodes 2 and 3, because remember this distributed load acts on element B right here. Okay? And so we have U2y is equal to minus 20,000 pounds. Okay? We also have the moment on node 2, which is 133,000. Pounds, feet, I think, or pound inches, sorry. Okay. Sorry, this is not U2y, this is F2y. Okay. Next we have F3y, and this was also minus 20,000 pounds. And then we have M3, which was the same as M2, but just opposite sign. Okay. Oh, sorry, this was negative, and then this one is positive right here. Okay. And so this was the result of our principle of equivalent work. Okay. And so if we actually plug this into, so if we plug these into our system, it would look something like this. And so instead of our distributed load, we would have loading that looks like this. We have 2 loads right here, and both of these are $20,000 or 20,000 pounds. Okay. And then we also have moments on these guys. So on node 2, we have a clockwise moment. Okay, and this is going to be let's see, 133,000 pound inches. Okay. And then over here we have a counterclockwise moment of 133,000 pound inches. Okay. And so, by applying our principle of equivalent work, we've converted that distributed load into these nodal loads, and now we can just kind of follow the same process as we did before. Okay? And so from here, we can basically write out the element stiffness matrices for all the elements. There's only 2 in this case, and then assemble the global system, apply our boundary conditions, and then we can solve. Right? All right, any questions on this? Okay. Okay. And so, as you know, with these frame equations, the matrices get really, really big. But I'll write out the element stiffness matrix, at least for element A, just so you can have a point of reference when if you want to do this on your own. Okay? Okay. And so element A, our angle here is 45 degrees. Okay? Which is kind of obnoxious because it's you know, not a nice, the cosine and the sine of this angle is going to be not a very nice number, right? And then to help us out with the computations, let's compute some of these constants. Okay. So first we have 12i over L squared. It's going to be 0.185 inches squared. Okay. We have 6i over L, and this is 23.57 inches cubed. Okay. And then we have E over L is equal to 1.179 E5 pounds per inches. Okay. And so you plug all that into our expression for the element stiffness matrix for a frame, and you get something like this. Okay. Oh, you know, and I think I mentioned this in the announcement that I sent out too. But for homework 2, because you know they involve a lot of these frame problems, I've uploaded a Matlab script to basically help you compute these guys. And so computing the element stiffness matrices for a frame is, you know, way more tedious than it is educational. And so, you know, I don't want you guys just sitting there for hours just punching numbers into your calculator. And so the way you use that script is you basically at the very top of the script you can input all the properties like the Young's modulus, the moment of inertia, the length, and the angle, and all that stuff. And then you just run the script, and then it'll compute your K for you. And then you just read that off, just whatever that K is from the console. So, you know, please use that script. You know, I don't want you sitting there for, you know, hours computing these things, because it gets really tedious, especially for systems with, you know, 3, 4, 5, 6 elements. Then, you know, you're going to sit there for hours, and it's not going to be useful. And then you're going to find out that you made some small sign mistake somewhere over there, and you know, it's just not a good use of your time. So, you know, please use the script just to kind of save yourself some sanity doing these problems. Okay. Okay. And so I'll write out kind of the first couple columns here, as much as I can fit onto this page. But the rest of it you can see in the posted lecture notes. So first we have 4.42 E6. Right, 7.07 E6 minus 4.28 E6 minus 4.42 E6, okay, minus 7.07 E6 minus 4.53 E4, okay. All right, so that's the first column. Okay. And so fun fact, you know, I wrote these lecture notes before I wrote that MATLAB script. And so I basically computed the first one by hand. And I said, this is awful. And then I stopped after this. So that's why in the lecture notes, you know, you'll only see one element stiffness matrix in there, because, you know, even I think that this is kind of really tedious to do. So. But you know, that's why finite elements traditionally we let computers do it, because computers are really great at doing these tedious calculations, and I like to think that they're happy to do so too. But you know, computers don't have feelings, so it's okay. All right, so then we have 1.15 E7, 2.64 E6, minus 7.07 E6, minus 1.15 E7, okay, and 2.64 E6, okay. So I'll do one more column here. So we have 1 minus 4.28 E6, okay, 2.64 E6, 6.34 E8, 4.28 E6, minus 4.28 E6, and 3.17 E8. And then, you know, I'll put ... here because it's continued on, okay? But again, you know, this is all just the same process. You know, it's just more calculations involving it. But, you know, we've done this, you know, so many times over the last few weeks that, you know, It's the same thing. Element stiffness matrix, global system, boundary conditions, solve. Same process kind of over and over again, just with some more calculations. Okay. All right, any questions on this? Okay. I guess when robots take over the world, they might find this lecture video and say that I will be the first to go for my comments on computers don't have feelings. Okay. And so, you can repeat this process for element B. You assemble the global system, apply the boundary conditions, and then you get the following solutions. Actually, let me state what our boundary conditions are. Okay. So just to be kind of clear. All right, so we have two Dirichlet boundary conditions, or two constraints. And so the first one is that node 1 is fixed. And so we know that if we have a fixed boundary condition, this constrains all 3 degrees of freedom. So that means both the x displacement, the y displacement, and the rotation are going to be 0 at node 1. Okay. So this means that u1y, u1x, u1y, and theta 1, all these guys are going to be equal to 0. Okay. And so once you assemble the global system, the first 3 rows in the matrix are going to be replaced by these guys. Okay. They're going to be replaced with our row of all zeros and the 1 on the diagonal. Okay. And so the other Dirichlet boundary condition here is that we have node 3 is fixed. Okay. And so again, that means all 3 deformation degrees of freedom are going to be 0. Okay. Right. So these are our Dirichlet boundary conditions. And so we also have Neumann boundary conditions. I remember our Neumann boundary conditions are simply just our modes. Okay. And so we had 2 different. We had a distributed mode here, and that transformed itself into 4 nodal modes. Okay. And so the first one that we'll apply is on node number 2. So on node number 2, we have a force in the y direction. Okay, so that was minus 20,000 pounds. Okay. And then so M2 is minus 133,000 pound inches. Okay. And actually, these are the only loads that we're going to apply. Okay? And so I know that we also had nodal loads on node 3, right?
Professor?
Yes.
Sorry, just because I can't see the image from before, is it a negative for the M2 because it's in rotation?
Yes, yes. So the M2 is negative because it's a clockwise moment. So whenever we have something that's clockwise for a moment, then we add a minus sign, just because that's just the sign convention that we use for that.
Professor?
Yeah. Mm-hmm.
Should it be minus 160,000 pound inches?
Yes, you are right. Yes. Okay. Oh yeah, I overlooked that in the notes.
Thanks.
Yeah. Yeah, so there was, I think this is, so when I first computed, it was 133,000 pound feet, and then when you, or 13,000 pound feet, and then when you convert it to pound inches, then it becomes 160,000. So, yeah, you're absolutely right. Yeah. Okay, thank you. Okay. Okay, and also, okay, so we also have loads on node number 3, right? So we also had, a minus 20,000 pounds and a positive 160,000 pound inches. Okay? But, on node 3, you can see that we also have a Dirichlet boundary condition on node 3 as well, right? And so I think this is probably the first time that we've seen this, where we have both a Neumann boundary condition and also a Dirichlet boundary condition on the same node. Okay? And so when you have these guys happening at the same time, the question is, which one do you specify, or how do you actually account for this in the matrix? And so the answer is that the only one that you actually account for is the Dirichlet boundary condition. Okay. And so when you have a Neumann boundary condition that's being applied on a Dirichlet node, you just don't apply the Neumann boundary condition at all. And the reason for that is because you don't want to apply both at the same time, because otherwise you're going to end up with a very, very strange result. And so when you have both of these applying, you can kind of almost think of the Dirichlet boundary condition as like a dominant gene, and so that's basically going to dominate the expression of the boundary condition. So first of all, you never want to apply both, but when you do have a case where you have both a Dirichlet and a Neumann boundary condition applied on the same location, you only apply the Dirichlet boundary condition because those are kind of a much stronger condition than the Neumann one. Okay. All right. Any questions on these? Okay. And so you plug all that in, and you make your system, and you end up with the following solutions. And so you get U1x is equal to 0, U1y is equal to 0, theta 1 is equal to 0 radians. Okay. Right, so then we have the deformations at node 2. Okay, so you have U2x, U2y, and theta 2. And so this is going to be 0.0033 inches. This will be minus 0.0097 inches. Okay. Theta 2 is equal to minus 0.0033 radians. Okay. And then for node 3, because we had a Dirichlet boundary condition, all of these are also 0. And so if you wanted to kind of finish up this problem, by yourself, this is kind of the reference solution that you should do. Okay. Any questions on these? Right. So the question is, so the 20,000 pound downward force at node 3 doesn't do anything. So that's correct. Yes. And so that 20,000 pound downward force, it doesn't do anything to the deformations, but it does add to the reaction forces too. So like if you can imagine, you take your pen and you kind of like push it into the table and you keep pushing it, right? Maybe if you're strong enough, you can actually break your pencil, but in reality, because your table there is fixed, the pencil is not going to move, right? But as you apply more and more force, what's happening is that the table is inputting a much bigger reaction force to kind of prevent the movement, and also that force is also being applied through the length of your pencil, and so the pencil itself experiences more stress. And so just for this problem, since we were solving for just the displacements, we didn't account for that 20,000 pound force at the node 3, but it does have an effect on the reaction forces and also the stresses that the structure feels. Yeah. Okay. All right. And so that's the basics of frame problems right there. So I know I skipped a lot of the steps in the class because it's these matrices just kind of get really big, and I think if I had a whiteboard in the class, I think it'd be easier to kind of write a big system. But because I'm kind of limited here, and I don't want the in-class notes to get too messy, I did skip a lot of those steps. But definitely go back in the lecture notes when you have time, work out some of the examples yourself, and see if you can kind of get kind of the same matrices that I did. Okay. And so that's frame equations. But before I put the closing thoughts on this chapter, and we jump into the Matlab, I do want to say a few things about just the application of Dirichlet boundary conditions. Okay. And so up to this point, you know, in the notes, you know, whenever you have a Dirichlet boundary condition, the way I've told you how to take it into account is to basically replace an entire row in the stiffness matrix, and then put the Dirichlet, and just make everything zeros except for the 1 on the neck. Okay? And so the method that that I've been teaching you, I don't know if it has a specific name, but the way I call it in my head is I call it kind of the row replacement method. Okay. But you know, if you did end up picking up the Logan textbook, and you've been kind of reading through the book and seeing how they do their Dirichlet boundary conditions, you'll probably notice that they do it a little bit differently. And so I kind of wanted to spend some time talking about those differences, and also kind of talk about kind of why I do it like this. Okay? So in the book, when they apply a Dirichlet boundary condition and they say that this node is going to be fixed, what they do is that they actually eliminate the entire column and the entire row involved with that degree of freedom. Okay? And so, you know, again, I don't think this has an official name, but then what I call it is kind of the row and column deletion method. And so, you know, both methods are fine for everything that we've been doing. And you know, after I show you kind of how the row and column deletion method works, you might get upset a little bit, because it ends up making your global system a lot smaller in a lot of cases. But there is a good reason I'm teaching you the row replacement, especially, you know, it's going to be useful once we get on to other equations. We'll talk about kind of general differential equations after the midterm, but we'll also be solving things like the heat equation, where, you know, when we apply Dirichlet boundary conditions there, row replacement will actually be a lot more convenient than the row and column deletion. Before I do that, are there any questions on this? Okay. Okay, so let me just kind of illustrate the row and column deletion method if you haven't seen it yet, right? And so let's say that we, you know, let's just say we have a truss problem, okay? And we have 3 nodes. And so with 3 nodes, we have 6 degrees of freedom. So we have a 6 by 6 global stiffness. Okay. And let's say in this case, we have node 1 to be completely fixed. And so if node 1 is completely fixed, then normally we just replace this with zeros like this and a 1, right? And then we just are along our merry way, right? But what the book tells you to do is that if you know, node 1 is fixed, you know, then there's no reason that there's actually no reason to actually keep it in the stiffness matrix. And so what they do is that go look at all the columns associated with U1x. So that's this column right here. I'll use a different color. Okay. Okay. And so U1x is associated with that column right there. And then they say go to the row that's associated with U1x, which will be the entire first row. Okay. And just cross it out. Right? And then do the same thing for U1y. So let's cross out the entire column for this. And the entire row for that. And so this is what you would do if node 1 was fixed. Okay. And so after you do those deletions, all you're left with is just this system right here. Okay. And this system is nice because it's, instead of being 6 by 6, this guy's only 4 by 4. Okay. And so your new system would look something like this. So U2x, U2y, U3x, U3y. Okay. And so, by virtue of only being a 4x4 system, you only have 16 matrix entries to in order to fill in, right? I'm just putting, so these are circles, these aren't zeros. I'm just showing that there's 16 of them, okay? Versus if you did a 6x6 system, a 6x6 system has 36 entries, right? And so if you compare 16 entries versus 36, that's a huge amount of difference in writing. And so you're probably wondering, why don't we use this method right here, which, results in way less writing and is generally a lot easier to deal with, at least for hand calculations, okay? And the reason is because of, the reason you can do this method for these kinds of problems is that whenever we had a Dirichlet boundary condition, the Dirichlet value there was always 0, right? And so that's just kind of the nature of structural problems, where if you constrain a node, then you say that this node cannot move at all. And so the displacements and sometimes the rotations are always going to be 0. Okay? But later on, we're going to come across problems where the Dirichlet value is not 0. And in those cases, you need to have you need to use the row replacement method in order to do it. You can do the non-zero Dirichlet boundary conditions with this method as well. It's just a lot more annoying because then the Dirichlet boundary condition goes to the other side of the equation. But I'll show you what I mean in the next slide. I think I'm getting a little ahead of myself. Are there any questions on this before I turn the page? Okay. Okay. And so the row and column deletion method only works well when Dirichlet value is 0. And what I mean by Dirichlet value is basically the value that we're specifying for that degree of freedom, okay? And so what you've noticed for all the problems that we've been doing so far is that when we say that we have a Dirichlet boundary condition, we say that, like, u1x is equal to 0, u1y is equal to 0, right? And so the fact that 0 is always on this side of the equation right here means that we have a 0 Dirichlet value, okay? And so for structural problems, this is the case 99% of the time. There are special cases where it's not the case, but because we have a 0 Dirichlet boundary condition, you can take kind of a shortcut and do the row and column deletion method. But there will be cases that we'll see later on where this is not the case. Okay? And so let's take a simple like heat transfer example. Okay. And so let's just kind of do the simplest heat transfer problem you can think of. And so let's have a rectangular plate. Okay. And then let's say on one side of the plate we have a certain temperature. And so let's say that we have 50 degrees C, okay, on one side. And then on the right-hand side, we have 25 degrees C. Okay. And so the fact that we're going to directly specify the temperatures on these two sides of the plate means that these are going to be our Dirichlet boundary conditions. Okay. All right. And so if you call this guy like T1, okay, we'll call this guy Tn, where n will be like kind of the number of elements in that direction. Okay. Oh, there's a question in the chat. So question is, with the roller system, you could say 6x6 goes to 5x5 then. Yeah, that's correct. And so with the row and column deletion method, you only delete the degrees of freedom that are constrained. So with the roller support, since you're only constraining one of the degrees of freedom, you would only delete one of the rows and one of the columns. Yeah. Okay. All right. So now our Dirichlet boundary conditions here are, you can see that they're, they have the same form where we're directly saying that the temperature at these places has to be a pre-specified value, but instead of being 0, these are things that we have 50 and we have 25. And so, applying these boundary conditions with the row replacement method is actually pretty convenient. And I'll show you how to do it on the next page. But if you want to do the row and column deletion method, you know, with these non-zero Dirichlet, it becomes, it's not that annoying. It's just sometimes it's just kind of easy to forget. And so I really like the row replacement method because yes, it makes your systems a lot bigger, but then you can see just by one glance at the entire system where all your boundary conditions are. And I think it's kind of a lot easier to kind of see. Okay. Okay. Any questions on that? Okay. And so let's see how this would look like with the row replacement method. And so let's say that we want the boundary condition for T1. Okay. And so with the row replacement method, you know, we're still going to do the same thing on the left-hand side matrix. And so we're going to say that, you know, we're going to replace this entire row with a one on the diagonal and zeros everywhere else. Okay. Okay. And normally on the right-hand side, when we do this, you know, we just put a 0, and because that's our Dirichlet condition. But in this particular case, you know, our Dirichlet value is not 0; it's actually 50, right? Okay. And so you can do the same thing for Tn. Okay. And so let's say that we have Tn down here, okay. And then this entire row will be 0, 0, 0, 0, 1. Okay. And then on the right-hand side, we just set the Dirichlet value, which is 25. Okay. And so when you have, so once we get later on and we do have cases where our Dirichlet values are non-zero, you know, the row replacement method, it adapts to it really well, because all we have to do is, you know, do the same thing that we did on the matrix, just replace the entire rows with zeros and the 1. And then on the right-hand side, we just put the Dirichlet value there. So, you know, I know it makes our systems now a lot bigger than they have to be, you know, especially for the gargantuan ones, which are like, you know, 16 by 16, you know, 18 by 18, 21 by 21, you know. I know it would help tremendously to reduce that in size, but you know, this is kind of the reasons I do this. Okay? But with that said, you know, for the homework assignment and for, you know, even for the midterm too, you know, because we're doing all structural problems where, you know, the Dirichlet value will be 0, you can use whichever method that you want. So you can use either the row replacement method, which is what we've been using, or you can use this kind of row and column deletion method to kind of save yourself some writing. Okay. And so the only thing that I ask is that no matter which method that you choose, just make sure to show all your work. And so if you're going to use the row and column deletion method, you know, explicitly show me the global matrix and then put you know, lines through the rows and the columns that you're going to delete because of that. Just so I know that you're applying. It's really difficult to give partial credit on, you know, on problems where you don't show that much work, because I don't really know your thought process behind that. So, you know, not only for this, but, you know, for everything, just, you know, every calculation that you did, everything that you punched in your calculator, just write it all down. And, you know, that's a lot easier for me to create. Okay. All right. Any final questions on this? Okay. And so that's it for the frame equation notes, right? And so from here, let me adjust my setup. What we're going to do is we're going to start implementing a finite element code. Okay? And so, you know, actually you can implement a finite element code for anything that we've done so far. But what I thought we'd do together as a class is the most difficult one, which is the frame equations. And then from there, you know, it'll be easier to write codes for the other ones as well. So let me stop sharing on my iPad. Okay, let me start sharing screen here. Okay, so that's my email. That's my other email. I don't know why I went to my other email instead of opening up Matlab. And so, you know, before we start, you know, I would, you know, what I've uploaded onto Canvas is basically the our starter code here. And so why don't everyone take a minute and go to the Canvas site and go to the week 6 for Canvas. And what you'll see at the bottom of the page there is a starter code. So it should be called frame FEM starter.m. Okay, so it should look like this. So frame MATLAB starter code. And so when you download that, you should get a code that looks like this. Right? And so what you'll see from this code is that I've already implemented kind of the basic structure of the entire code, but I've left a lot of key parts left blank. So they're called to do right here. Okay? And so what we're going to do for the rest of today and for Wednesday is we're going to work through this together and kind of talk about what you need to do to fill in these code segments. And while everyone's doing that, I've also uploaded some PowerPoint slides as well, okay? Just to kind of help you out, because it is going to be, a process to kind of go through these. So, once you're, if you can't finish in class, or you want just a reference for kind of my thought process behind this, you can reference the slides as well, and that's kind of my my motivation for that. Okay? And so I'll give everyone kind of a minute, download the starter code, maybe switch computers if you have to, and then we'll get rolling in maybe a couple minutes. And while everyone's getting that ready, I will comment and say that this implementation of the frame equations here, this is certainly not the only implementation that you can do. Actually, there's a ton of ways to actually make this a lot more efficient, both in terms of just pure lines of code, you can make this code shorter by a lot, but also in terms of memory usage, you can make it faster. And so the code that I'm showing you here, this is definitely much more of an educational code, just because I try to break it down kind of step by step as much as I could. But there's definitely a lot of things that you can do to improve it. So if you want a good activity that you can probably look into, if you're interested and you have some spare time, is to look at this code and say what are some ways that it can be improved. And all those improvements that you implement in this code, probably a lot of commercial codes will do the same thing as well. Okay, so did everyone get a chance to download the starter code? I have the slides here, so you don't have to follow along with the slides, but I just want to make sure everyone has the starter code on their MATLAB, just so that they can follow along. So is everyone able to download the code and open it in MATLAB okay? Okay. So I'm going to get rolling. Okay, so I'll have this kind of set up right here. I'll have the slides on the left and the code on the right, and basically everything that says to do, we're going to fill in, but we'll do it together. So, that you can take a scan through the code right now, but we're going to do everything that says to do together. Okay. Okay. So let's start going through the slides. Right. So just as a basic introduction, so far, we've been learning what's called the direct stiffness method to perform finite element analysis on structural systems. So, we've gone through several different element types. So we learned, first thing we learned was spring elements. Then we learned truss or bar elements. Those are kind of the same thing. Then we learned beams, and then we just finished up doing frames. Okay. And so, with the direct stiffness method, you can do a lot of the calculations by hand, but as you can start to see with the frame equations, it starts to get really out of hand, and it starts to get really difficult to do these programs. Okay? And so what we're going to do here is we're going to implement a code to solve these direct stiffness problems for us. Okay? But it's not going to do all the work, so it's not going to telepathically, know what problem you're doing. And so you do have to input some things, like things regarding the geometry, the material properties, and the boundary conditions. So those things you have to do manually. Which is, is not that different from any other code. Like, when we did ANSYS, we did have to tell ANSYS what our geometry looked like, what our material properties were, and what our boundary conditions were. Okay. But then, all the heavy lifting, all the matrix creation, assembly, changing the matrix and stuff, all that will be handled automatically by MATLAB. So all the kind of, tedious calculations we're going to let the computer do. Okay. And so I know, there's a lot of anxiety, I think, in the class for, doing MATLAB. So, I do want to say that, even though it's a code and it's, looking at it right now, it looks pretty intimidating, like 200 something lines of code. Even though it's a pretty decently sized code, I think, compared to some other ones, I don't want you guys to forget that, I've been kind of hammering home the exact same process, the last few weeks on purpose. And so that, I want you to draw the connection between the process that we use for the hand calculations and how that process translates into code. And so we're just following the same process. We're just kind of teaching a computer to do the same thing with the code, okay? And so just to kind of summarize this process, the first step is we're going to compute all the element stiffness matrices for all the elements. Then we're going to assemble this element stiffness matrices into the global system. Then we're going to apply the boundary conditions and then just solve. Okay? And so, it's going to take a bit of time to implement this first code. So probably, definitely for the rest of today and probably for a lot of Wednesday too. But once you have a code like this implemented, you can actually use it to solve some very complicated problems that, just by hand would just not be practical at all. Okay. And so, even though this is a relatively, compared to, probably the code base of ANSYS, which probably, tens of thousands, hundreds of thousands of code, this code here is relatively simple. But a lot of the same conventions are followed by those commercial codes and a lot of research codes actually too. And so I modeled this code after a lot of the research codes that I've worked on in graduate school, and I continue to kind of look at myself. Okay, and so kind of I think the biggest thing that we're going to have to implement for code is the use of data containers. And so if you've coded a lot before, you're kind of familiar with the idea of variables and different variable types. But it's something that's kind of important to know. Okay. And so the idea with the data container is that we need to basically define variables and define matrices and define vectors that's going to hold all the necessary data for these problems. Right? And so, to kind of draw the analogy by hand calculations, this would be the same as, writing down a piece of paper that the Young's modulus is this, or that the area is this, or like the moment of inertia is this, or even just simply as, how many elements and how many nodes that are in the system too. Okay. And so, all of this information needs to be encoded into variables so that the code can actually refer to them back later and get the proper values and access them when it needs to. Okay. And so I'm going to do my best, throughout these slides to kind of visualize these data containers, because some of them, a lot of them are just going to be simple vectors and simple matrices. But I think it really helps to kind of visualize what's in these data containers and what's the structure of them. Okay. Okay. And then also, I know everyone's down with the starter code, so we don't need to do that. Okay. Okay. And so throughout this this code, what I'm going to the example problem that we're going to be solving for is this one right here. And so this is the example problem we actually did in class last Wednesday. So we basically just have a 3-element frame, and so we have elements. I don't like this because they use numbers for both the elements and the nodes, but we have elements like, you can consider this element A, B, and C, and nodes 1, 2, 3, and 4. And here's all the properties, okay? And here's the boundary conditions. And so, I picked this problem because, we have the solution already for the hand calculations. And so once we implement everything in our code, we'll be able to kind of just really easily check our solutions from there. Okay. All right, are there any questions so far? Okay. All right, so let's start implementing. Okay. And so let's start at just the very top of the code right here. So in the very first step that we need to do in any finite element code is we need to define the size of the problem. And oftentimes for a finite element code, the size of the problem is determined just by how many elements and how many nodes that you have in your system. Okay. And so if you compare this step to ANSYS, this is the step that we pick it up from right after the meshing. And so if you remember from ANSYS activity 1, when I had you guys develop the mesh for the plate with the hole, I had you guys write down how many elements and it was mostly just elements, but you could have also looked up the number of nodes as well. And so this number is always very important for finite elements, because this is going to determine the size of your problem, how big your global system is, how many calculations you have to do. Okay. And so the way we're going to do that for this code is we just are going to simply write in the number of elements and the number of nodes. Okay. And so if you go to your Matlab script and you go to the first section right here, you can see I've defined one variable called big N underscore EL. So this is the number of elements. And so if you go back to the figure right here, we can see that we have 3 elements. And so we can go ahead and fill in 3 right here. Okay. And then next, we're going to fill in the number of nodes. And so this is going to be 1, 2, 3, 4. So we're simply just going to replace this to do with 4. Okay. All right. And so defining the problem size, this is kind of the first step that you do for finite elements. Normally, the first thing you do before this is meshing, but because we're working with direct stiffness, the mesh is kind of already made for us. So all we have to do is just kind of define how many elements and how many nodes are in our system. Okay. Okay. And so that's hopefully pretty straightforward. Okay. And so the next thing that we have to do is kind of define the geometry for our problem. Okay. And so the first thing that we have to do is we have to define how our elements are connected with each other, right? And so we're going to be working with this vector right here called connectivity, okay? And so because now what we've told the code is that, all right, we have 3 elements and we have 4 nodes, okay? But in order to proceed with the rest of the code, we need to basically specify how the nodes are going to be connected with each other, okay? And so there's, this is kind of one thing where there's kind of a lot of ways to do this. But this is kind of the way that I've been taught on how to organize kind of element connectivity. Okay? And so the way that I've structured this is that you can see that I've created a matrix right here. And so I've created a matrix called connectivity, and it's going to be a matrix that starts at all zeros. And the number of rows in this matrix will be defined by the number of elements. And so that's NEL. And then the number of columns is going to be 2. Okay. And so you can kind of think of this as the connectivity matrix. And the way that it's organized is that each row in the matrix corresponds to a different element, okay? And then in the 2 entries or in the 2 columns, what we're going to do is we're going to specify, which nodes that this element is connected to, okay? And so just as an example, let's take element 2 here, okay? And so element 2, you can see right here, is connected to nodes 2 and to nodes 3, right? So on the left-hand side, it has node 2, and on the right-hand side here, it has node 3, okay? And so the way that we're gonna express this in the code is we're gonna go to this row right here, and so we're gonna go to connectivity 2, 1, and we're gonna say that this is the row that corresponds to element 2, and so we're gonna say that this is equal to 2, because element 2 is connected to node number 2 on the left, and on the right-hand side here, we're gonna set this equal to 3, because on the right-hand side of that node, we're going to be connected to node number 3. Okay. Okay. Right. And so that's how you would do this for the first one element in the system. And so what I want you guys to do is to kind of fill in the connectivity matrix for all the other ones. Okay. And so here's the answer for you right here. But you can basically have all the information here to fill this in. So connectivity 1, 1, so this is going to be the first node of element 1, right? And you can see up here the first node of element 1 is going to be node number 1, right? And then this connectivity 1, 2 is going to be the second node of element 1, and so this is going to be 2. Okay. And then let me go back to here. And then now we can do the same thing for element 3. So element 3, the first node that's connected to is node number 3. And then the second node that is connected to is node number 4. Okay. All right. And so what we've defined in this connectivity matrix is to say that element 1, which is the first row of this connectivity matrix, that's connected to nodes 1 and also to node 2. Okay. And the second row of the connectivity matrix, which corresponds to element 2, this is going to be connected to node number 2 and node number 3, right? And then same thing for element number 3. Okay. And so I think this is definitely one of the more I think abstract, I guess, data containers. But this is kind of one way to basically tell the program or tell MATLAB, these are how our elements are connected to each other. All right. Any questions on the connectivity matrix?
So if we have more than 3 elements, we would just increase the number of lines for the connectivity.
Exactly, right. And so if you have 4 elements here, you can do you know, element 4 like this, right? So this would be 4, 1 and 4, 2. Okay. And so let's say that we had one element that goes from node 1 over here to node 3. So we have kind of a cross element that goes like this. Okay. And so the element connectivity for that one, so we call that element 4. And so on one side that would be connected to node number 1. Okay. And on the right side that would be connected to node number 3. Okay. Because those are the two nodes that this element would be connected. This theoretical element would be connected to, just like that. So yeah. So if you have a problem with more elements, you just add more rows to this guy until you have one row for every element in your structure. Mm-hmm. Yeah, great question. All right, any more questions on this? Okay. Okay, and so the next thing that we're going to fill in is all of the material properties for the elements. Okay, and so since we're doing a frame equation, each element here will actually have 5 different properties, and so we need to specify the Young's modulus, we need to specify the area, we need to specify the moment of inertia, we also need to specify the length, and we also need to specify its angle, so how much it's rotated. Okay, and so you can see I filled in most of the code for you. So what I've basically done is I've defined vectors that hold these properties, okay? Or you can think of them as arrays if that's what you're more familiar with. And then each entry in this vector or this array is going to hold the property for that element, okay? And so you can see here, you know, for element 1 right here, and the way we're going to specify the Young's modulus for that is we're going to say that E prop at 1 is equal to whatever the Young's modulus is for here. So in this case, it's 30 E6. Okay. Right. Next, we're going to have the Young's modulus for element 2, and so this is going to be 30 E6 as well. Right. Next, we have the Young's modulus for element 3, which again is going to be 30 E6. Okay. And again, if you had kind of multiple, if you had more than 3 elements here, you would just add additional rows here. So if we have, you know, a 4th element, we're going to have E prop 4. Okay. And if it had, and let's say that it had a different Young's modulus, so say it's, you know, 20 E6, you can specify that. You can do the same thing if you have a 5th element, right? And so you can add basically as many rows here as you need. Okay. And the nice thing about this this part of the code here is that this matrix or this vector right here will be automatically sized based on the number of elements because we specified this at the top of the code. Okay. And so for this next part, I want you guys to go ahead and fill in the rest of the area, the moment of inertia, the length, and then the theta for each one as well. Okay. So I'll give you guys kind of a few minutes to go ahead and fill that in. Okay. Okay, so slide 10. All right, so I'll leave it here just so you guys can see. Okay. And one important thing for the theta, once you get down there, is that the theta, you know, Matlab doesn't recognize degrees. I think you can set it to be, but the default is that it recognizes radians. And so when you're putting in the thetas for each of the different elements, make sure you put it in radians, not in degrees. Okay. And also the length as well. I know it says 10 feet here, but we want to be consistent in our units. So make sure you put this in inches. All right, so did everyone get a chance to fill in all the properties for the for all the different elements? Okay. Okay, so question. Yeah, so we're going to do sine and cosine later. You mean cosine d sine d? Yeah, actually, if you want to, I actually didn't even know that those were a thing. I can kind of guess what those things are. And so if you want to do cosine d sine d, which I'm guessing is cosine and sine using degrees, then you can do that as well. And so I have it implemented with just regular cosine sine, but if you want to do cos d or sine d, then that's you can definitely do that too. Yeah, just kind of remember which one that you use for which. Okay, so that's all the material and geometric properties. Okay, and so we're still kind of in this first section of the code here where we're kind of still defining the problem. Okay, and so if you kind of think of it from the computer's perspective, the computer also kind of has to learn what your problem looks like. So when you're doing things by hand, the way that you kind of learn about the problem, that you look at the figure, you look at the properties, and you kind of read the problem statement, right? And so remember, a computer doesn't have the ability to do that, because remember, computers don't have feelings; they can't think, right? And so what we're basically doing is we're defining in the code how we want the computer to see the problem. And so we're still kind of defining the problem for the computer here. First thing, we define the size of the problem. Then we define how all the elements are connected. We define all the properties for all the elements. And then the next thing that we need to do is to define the boundary conditions. Okay, okay, and so I'm going to do this in a little bit of a a strange way, but it might seem strange at first, but it's this is kind of the industry standard for how to do this. Okay, specifying the boundary conditions kind of goes in two steps. And so the first thing that we have to do is we have to define, or we have to specify which nodal degrees of freedoms will have the boundary condition. And so you can kind of think of this as which row in our global stiffness matrix will have, will need to be modified. Okay. And then the second step, which we'll do for the Neumann boundary conditions, is we also need to specify the value for that load as well. Right. And so remember, our Neumann boundary conditions, we not only do we need to know what row to put it in, but we need to know what value to actually put in the right-hand side matrix. Okay. And so this part can be really tricky because, especially for frame problems, each node actually has 3 degrees of freedom. And so if we want to specify, a load or something on like the x degree of freedom on node 2, that's going to be difficult to do because we need to know which row in the matrix is that going to correspond to. Okay? And so what we need to do in these cases is to have kind of an index formula. Okay. And so basically, so in this particular problem, remember we have 4 nodes here. Okay, and each of the nodes are going to have 3 degrees of freedom. An x displacement, a y displacement, and rotation. Okay, and so the total amount of degrees of freedom, or basically the total number of rows and columns in our global system, will be 3 times the number of nodes. So it's going to be 12. Okay? And so if we number each of those degrees of freedom 1 through 12, and we kind of go in our typical order, then we need to know which index or which row in that matrix is going to be modified. Okay, and so what I've shown you here is that you can easily just count it up if you want, but for bigger, more complicated cases, it gets pretty difficult to count which degree of freedom is going to be. And so what I've shown you here is kind of an index formula to basically help you out. Okay? And so, the way to use these formulas is to basically, let's say that we want to specify a Dirichlet boundary condition on, the y degree of freedom for node number 1. Okay. And so the way that you can use this formula is you want to compute the index or the row in the matrix for that degree of freedom. Okay. And so the way you use this is that every time you see I in these formulas, that's where you plug in the node number. So for node number 1, you would plug in I is equal to 1 here, okay? And then the row or the index for that row will be 3 multiplied by 1 minus 1 plus 2. And so we have 3 times 0 plus 2, and that's equal to 2, okay? And so I have another example here. So let's say that we want to get the row associated with the y displacement of node 3. And so we plug in I is equal to 3 into our second equation here. And we get 3 times 3 minus 1 plus 2, and that's going to equal 8. Okay, and so from this equation, we know that we need to apply a boundary condition on node number 8 in the system. Okay, And so we're going to basically use this to specify all of the boundary conditions that we have in this figure right here. Okay. And so I think, you know, this is kind of a good place to stop, just because it's 6:45 right now. And so on Wednesday, we're going to basically pick it up from here and then implement the rest of the code from there. Okay. But you know, that's all we got time for today. So so thank you everyone for tuning in. You know, we'll come back to this MATLAB stuff on Wednesday. So you know, make sure you have MATLAB open and have this script open. If you want to jump ahead, you can definitely do that. You know, definitely feel free. But if not, we'll pick it up from here. So thank you everybody, and I'll see you guys on Wednesday. Yeah. So on Wednesday, we're going to continue this example. So we're going to implement basically the rest of this code on Wednesday together.